Whoa, look at this. Look at all this energy we've got now. We've got kinetic energy, 1/2 mv squared. We've got rotational energy. We've got gravitational potential energy. Remember this guy? Elastic potential energy. Now we have this crazy electric potential energy. And then here's another way that we measure energy, especially in like high energy labs, even though that's a very small voltage there. One electron volt, this is incorrect. 1 electron volt is equal to 1.6 times 10 to the negative 19. This is so bad, it's not even funny. Hold on a second. I'm going to fix that sucker right here, right now. So let's edit. Oops. Because this is 1.6 times 10 to the negative 19 joules. That should be a J there. I have no idea why. Let's end the show so I can fix that. So right here, that should be a J. Okay. Whatever. So I can't fix it. All right, so let's go back to the slideshow. That should be joules. I'm going to write it down right here. Look. Because here's the deal. 1 electron volt is equal to 1 electron, which is 1.602 times 10 to the negative 19 coulombs, times 1.0 volts. That's an energy. Notice I got coulombs times volts. Right? Coulombs times volts, coulombs times volts is energy. Right? So this is equal to 1.602 times 10 to the negative 19 joules. All right? That's what 1 electron volt equals. It's much easier working in electron volts. Like say we shoot a proton. Shoot a proton through a change in voltage of 50,000 volts. What's its energy? What is its energy? When you shoot it through that much voltage, what's its energy? Well, you can say, well, I got a proton which is just 1e, right? The charge on a proton is 1e positive. Okay, so you go 1e times change in 50,000 joules, 50,000 volts. You go, oh, 1 times 50. So it's 50,000 electron volts is the energy. The actual joules of it, convert that to joules, I got to multiply by 1.602 times 10 to the negative 19 joules per electron volt, per 1 electron volt is equal to 50,000 electron volts. The electron volts cancel. This calculation, for some reason, I'm multiplying, is equal to, that calculation is very difficult for people. Very, very difficult. Especially when they don't have a calculator, like I'm scrambling for now. But here we go. So here's what it looks like. So you got 50,000 times 1.602 second e to the negative 19. Boom. 8.01 times 10 to the negative 15 joules. It's much easier using that figure. That's why we use electron volts. Okay? All right, so now let's do this. And then we'll stop. If we do this much, then we can stop, okay? So it says a particle has a mass of 1.8 times 10 to the 5th kilograms, 10 to the negative 5 kilograms, and a charge of 3 times 10 to the 5th positive coulombs. It is released from point A, so it's going to, it's released from point A and is flying towards point B. The only force acting on this particle is the electric force, and the electric potential at A is 25 volts greater than at B. So it's going to go, we could say it goes from 25 to 0 this way if we wanted to, because it doesn't matter. We're just looking at the change in voltage. We could say this is positive 50 volts and this is positive 25 volts. So the difference is positive 20, this is 25 greater than B, okay? What is the speed of the particle at B? What? If the same particle had a negative charge released from B, what would be its speed? Speed would still be the same because it's the same charge, same energy, same change in potential energy, converting that potential into kinetic energy. Are you ready to do this and see how this works? Because I'll be honest with you, when I first learned this was very confusing to me. So this is the only problem. We're going to stop here at this problem. I'm going to call it up. It's going to be the last thing that we do here. If we get this far on this, we're golden. Okay? So we got one more track to do, and that'll be this problem.